Every whole number bigger than 1 is either prime, divisible by nothing but itself and 1, or it breaks into smaller pieces. 7 is prime, 8 is 2 times 2 times 2, and somewhere out along the number line sits the largest prime anyone has ever found. We do not mean the largest prime there is. There is no largest prime there is. That was settled more than 2,000 years ago, and the primes run on forever. We mean the largest one a human being has actually pinned down, written out, and proven prime, with nothing larger yet confirmed. As of right now, that champion is a single specific number, and the first surprising thing about it is its size. Printed in ordinary digits, at a few thousand digits to a page, it would fill a stack of paper around 13,000 pages thick. Reading it out loud, 1 digit a second without sleeping, would take you about 95 days. So this number has 41 million digits, 41,024,320 to be exact. And the strange part is not just that it is huge. Plenty of huge numbers are easy to write. The strange part is that we know for certain that this monster has no factors at all except itself and 1, even though no person and no machine could ever divide it by hand to check. Over the next few minutes we will see exactly what the number is, the clever shape that lets us test something this large, who found it and on what, and a chain that ties it all the way back to the ancient Greeks. You might expect a record-breaking prime to look random, a wall of unpredictable digits. This one does not. It has an almost insultingly simple description. Take the number 2 and multiply it by itself 136,279,841 times. Then subtract 1. That is the whole thing. The largest known prime is just a power of 2 with a single unit shaved off the end. It helps to see why subtracting 1 matters so much. A power of 2 in ordinary base 10 is never anything tidy, but write it in binary, the language of bits, and a power of 2 is a 1 followed by a long row of zeros. Subtract a single 1 from that, and every digit flips. The leading one is gone, and what is left is a solid, unbroken run of 1s, with no 0 anywhere. So this record prime in binary is the simplest pattern you can imagine. It is 136 million 1s in a row, and not 1 0 among them. Numbers of this form, 2 raised to a power and then dropped by 1, are old and famous enough to have their own name. They are called Mersenne Numbers, and we will meet the man they are named after later. For now, the only thing that matters is the recipe. Pick an exponent, double 2 that many times, take 1 away. The champion prime is the Mersenne number whose exponent is that 136 million figure. 41 million digits, and you can describe it on a napkin. Here is a fair question. Out of all the shapes a number could have, why would the record always seem to land on this one, 2 to a power minus 1? Part of the answer is practical, and we will get to the test that makes it possible. But part of it is built into the shape itself, and it cuts the search down enormously before any computer even starts. The claim is this: for a Mersenne number to have any chance of being prime, its exponent has to be prime too. If the exponent splits into smaller factors, the whole Mersenne number splits as well, guaranteed, and you can throw it away immediately. You can feel why with a small case. 2 to the 6th is 64, so 2 to the 6th minus 1 is 63. 6 is not prime, it is 2 times 3, and sure enough, 63 is not prime either. It is 7 times 9. That is not a coincidence. Whenever the exponent has a factor, that factor leaves a matching factor sitting inside the Mersenne number every time, with no exceptions. So before testing anything, you can ignore every Mersenne number with a composite exponent. The hunt only ever has to look at exponents that are themselves prime, which is already a thin set out in the millions. The record exponent, that 136 million number, is itself a prime, as it has to be. Now, this is the place where it is easy to fool yourself, and getting it right is the difference between understanding the search and just admiring it. A prime exponent is required. It is tempting to round that up to, a prime exponent is enough. Plug in a prime, double away, subtract 1, and surely you get a prime out. For the very first cases, it even works. 2 gives 3, prime, 3 gives 7, prime, 5 gives 31, prime, 7 gives 127, also prime. 4 prime exponents, 4 prime results in a row. Then you reach the exponent 11, which is certainly prime, and the spell breaks. 2 to the 11th is 2048, so 2 to the 11th minus 1 is 2047, and 2047 is not prime. It quietly factors into 23 times 89. The exponent was prime, the result was not. So a prime exponent buys you a ticket into the lottery, but it does not win it. Most prime exponents, in fact, hand you a composite Mersenne number that just happens to be hard to factor. Out of all the millions of prime exponents we have checked, only 52 of them have ever produced an actual Mersenne prime. The shape narrows the field. It does not hand you the answer, so we are stuck with a real problem. We have a number with 41 million digits, and we need to know whether it is prime when there is no hope of trying to divide it by everything smaller. The thing that rescues us is a test built exactly for this shape, and it is almost shockingly simple to state. It is called the Lucas-Lehmer test, and you can run it by hand on a small case in under a minute. Start with the number 4. Now repeat one move, square what you have, then subtract 2, square and subtract 2, square and subtract 2, over and over. The only twist is that you do all of this not with the full giant numbers, but with remainders after dividing by the Mersenne number you are testing, which keeps everything a manageable size. After doing that, move a fixed number of times, 2 fewer than the exponent. You look at what you are left with. If it is exactly 0, the Mersenne number is prime. If it is anything else, it is not. Watch it work on the exponent 5, which should give us 31. Start at 4. 4 squared is 16. Minus 2 is 14. 14 squared is 196. Take the remainder after dividing by 31 and you get 8. 8 squared is 64. Minus 2 is 62. And 62 is exactly 2 31s, so the remainder is 0. We did the move 3 times, which is 2 fewer than 5, and we landed on 0. So 31 is prime, which of course we already knew. The point is the method. One simple loop, no factoring, no luck, and it scales. The same loop, run 136 million times on a fast enough machine, is exactly what certifies the champion. That is why the records are Mersenne numbers. They are the one shape with a primality test this clean. That test turns the search into something a lot of ordinary computers can share, and that is the second half of the story. Since the 1990s, there has been a single, sprawling volunteer effort aimed at exactly this, called the Great Internet Mersenne Prime Search. The idea is plain. Hand every spare machine a different prime exponent to test with the Lucas-Lehmer loop, let them grind away in the background, and pull the results. For decades, every new record came out of that shared net of home computers, each one quietly checking its assigned candidate. Nearly all of the largest primes we know were found this way, by people donating time on machines that would otherwise be sitting idle. The current record came in on the 12th of October, 2024. It was found by a researcher named Luc Durand, and the machine was not a single computer at all. It was a cloud of graphics cards, the same kind of chip built to draw video game worlds, thousands of them rented across many data centers and pointed at this one arithmetic loop. Those chips are extraordinarily good at doing the same simple operation over and over on huge numbers, which is precisely what the squaring step needs. After running through candidates, one of them came back with a 0 at the end of its sequence, and the answer it certified was 2 to the 136 millionth minus 1. The previous record, set back in 2018, had a mere 25 million digits. This one cleared 41 million. A jump of more than 16 million digits in a single step. These numbers have carried one name for almost 400 years, and it belongs to someone who never tested anything remotely this large. Mersenne Numbers was a French friar and mathematician, born in 1588 and died in 1648. He was less a lone genius than a hub, In the years before scientific journals existed, he wrote letters constantly, passing problems and results between the great minds of his day, stitching a scattered community together by mail. And in 1644, he did something bold. He published a list of exponents that he claimed gave primes of this 2 to a power -1 form, far past anything that could be checked at the time. His list was wrong in places. He missed some exponents that do give primes, and he included a couple that do not, mistakes that took other people centuries to fully sort out. But the audacity of writing down a claim that far ahead of any possible check is part of why his name stuck to the whole family of numbers. He pointed at a pattern long before anyone could verify it, and the pattern turned out to be worth chasing for the next 400 years. The friar who guessed, partly wrong, ended up with his name on the largest primes humanity will ever find for the foreseeable future. Now for the part that surprises almost everyone, because it reaches back 2,000 years before Mersenne, and ties his numbers to something the Greeks already cared about. The ancient Greeks were fascinated by what they called perfect numbers. A perfect number is one that equals the sum of all its smaller divisors. 6 is the first. Its divisors below itself are 1, 2, and 3, and 1 plus 2 plus 3 is 6 exactly. The next is 28, which is 1 plus 2 plus 4 plus 7 plus 14. After that comes 496, then 8,128. They are rare and they were treasured. And here is the connection. Every one of those perfect numbers is built directly out of a Mersenne prime. Euclid noticed, and Euler later proved completely, that you make an even perfect number by taking a Mersenne prime and multiplying it by a specific power of 2. 6 comes from the Mersenne prime 3, 28 comes from 7, 496 comes from 31. Every even perfect number that exists corresponds to exactly one Mersenne prime, and every Mersenne prime gives exactly one perfect number. So the modern hunt for record primes is, without anyone planning it that way, also the hunt for new perfect numbers. Finding that 41 million digit prime in 2024 also handed us the 52nd perfect number, a thing the Greeks would have recognized and prized, only now far too large to ever write out by hand. So the whole shape of it comes together. The largest prime we have found is 2 to a power -1, a Mersenne number, with a prime exponent of about 136 million. We trust it is prime because of one short squaring loop, the Lucas-Lehmer test, run on a cloud of graphics cards by a volunteer search, and the same number quietly gives us a perfect number, closing a loop the Greeks opened. It is worth looking at how this record has climbed. For most of history, the biggest known prime crept up slowly, a few digits at a time. Then the machines arrived. The largest known prime had 2 digits, then 3. Then in the 1950s it broke past 100. In 2008 it cleared 10 million digits for the first time. Now it stands above 41 million. Each leap is mostly a leap in computing power aimed at that same simple loop. And right beside all this certainty sit 2 questions nobody can answer. We do not know whether there are infinitely many Mersenne primes. We expect so, and they keep turning up roughly on schedule, but no one has proven the supply never ends. And we do not know whether a single odd perfect number exists anywhere. Every perfect number ever found has been even, every one tied to a Mersenne prime. But nobody has proven an odd one is impossible, and nobody has ever found one. If you remember one thing, let it be this. We can be completely certain a 41 million digit number is prime without ever dividing it once, yet we still cannot say whether its family ever runs out. This was one in a series on how one question gets settled, and which ones stay open. Stay for the rest.